The idea is if I had a graph, think Calc 1, I've got a graph and I'm just doing stuff here. Clearly, the most interesting places on the graph we always think of are where are the peaks and valleys. That's first and foremost. Intercepts, if I can get them, it's nice. Where I cross the y-axis is easy. Where I cross the x-axis might be a little bit of work, but I'm really interested in the peaks and the valleys. And one other place, that guy right there, which is where I change concavity. So there's an inflection point in there. And to find these, obviously, we need to take derivatives. We need to do analysis. I've spent the last 2 classes in my Calc 1 doing graphing concepts, and we did first derivative tests today. We're going to be doing similar things in 3 dimensions, so we have to kind of figure out how it works when we have multiple variables. But if this is y equals f of x, if you remember, I find these by finding where f prime of x equals 0. That's the main thing. Then we talk about intervals of increasing and decreasing and that sort of thing. Now, we don't really have an analogy for increasing and decreasing in 3 dimensions because we're going to be looking at surfaces. But in terms of this, that makes perfect sense. Then there's also the second derivative, and that's one thing I want to point out. So let's say that's A and that's B. Okay, so if f prime of A equals 0, and that's also f prime of B, then we say that A and B, we call them critical values or critical numbers. I have people in Calc 1 tell me they're critical points. That's actually an egregious error. A point is an ordered pair. X equal 2 is a value. It's not a place. It's a value. And critical values produce extrema. Extrema are the y values. The only points in any answer in Calc 1 is an inflection point, because that doesn't have a value. That is a point, that is a location. But people confuse vocabulary because they confuse it with Calc 3 vocabulary. In Calc 3, we have critical points because we have x comma y's that produce the extrema, which are in this case the z values. So we'll get into the language later. So if this is true, I knew about intervals of increasing and decreasing. Again, we're not going to do intervals of increasing and decreasing because we don't have intervals. We have, remember, our domain is now ordered pairs. But there's a second derivative test, if you remember, in Calc 1. And the second derivative test was if A and B are critical values, if f double prime of A is positive or f double prime of A is negative, I can tell you a lot about what's going on. Remember, if I have a horizontal tangent at A, this means I'm concave down. That would mean my second derivative is negative. Here, I'm concave up, which would mean my second derivative is positive. So we'd say if the second derivative evaluated at a critical number is positive, then you have a minimum. If it's negative, then you have a maximum. And that goes with the picture. If I'm concave down where I have a horizontal tangent, okay, that's got to be a maximum. If I'm concave up where I have a horizontal tangent, that's minimum. That's called the second derivative test. Now, that's what we use in Calc 1, but we don't always use it. A lot of times you use the first derivative test. The first derivative test in simple English is if I'm increasing, I'm flat, and then I'm decreasing, I have a maximum. If I'm decreasing, I'm flat, and then I'm increasing, I have a minimum. That's first derivative test. Again, that's simple. So how did you know in Calc 1 whether to use the first or second derivative test? Really is this: if each successive derivative is easier to take, like a polynomial, then second derivative test is easier than first derivative test. But if you have something that's more complicated and you've got chain rules and different things going on, if the second derivative is more complicated than the first, you'd rather use the first derivative test. It's actually whichever one's easier because they'll give you the same information. So that's what we did in Calc 1. So now I want to talk about something that you did last semester in 151. And that was you looked at conics, and particularly you did things like, rotation of axes and things like that. But I want to keep it just to the conics. When you looked at the conics, you had things of the form ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And you hated this guy here. When there was an xy term, that meant you had to consider there might be a rotation of axes. So what you did was, first of all, you figured out what is the shape. Then you figured out what is the angle of rotation. Then you had to do all this huge transformation, substitute back in there, do all of this crazy stuff to get the, the shifted thing and what it was. Well, if you were in my Calc 2, I'd say, yeah, that's all very interesting, but you're never actually going to do that ever. In fact, you're never even going to bother with the angle of rotation. The only thing you actually cared about is what's the shape. And which, by the way, is the fastest, the easiest part of the whole problem. The angle of rotation, that's not very hard to figure out. That's pretty easy if you remember cotangent of phi, right? A minus C over B. I don't need that. I'm never going to use that again. So I don't dwell on that in Calc 2. What I dwell on is what is the shape? And so if this was a conic, what you remember with, we did 4AC minus B squared, and you had three possibilities. It was greater than 0, it was equal 0, it was less than 0. Okay, for these A, B, and C. D, E, and F have no effect on the shape. They just affect whether I've shifted. If all of those were 0, it wouldn't make any difference. These coefficients just mean I'm going to move my center or I'm going to raise it up and down. They don't affect what the shape is, just where the shape is. Okay. In this case here, I had an ellipse. In this case here, I had a parabola. In this case here, I had a hyperbola. Okay, that's what you did hopefully in Calc 2. The most important part of this problem was identifying the shape, which was also the easiest part of the problem, but it was critical. Now you say, how can I do this? Well, let me give you a really simple example of where this really is effective. Let's suppose I had the following. I have, I'll keep it simple. I've got 2x squared plus, I want this to be easy. Yeah, I'll use 2. 2x squared plus plus hold on. I want the numbers to be ridiculously easy. Actually, oh, you know what? I'm not going to put coefficients. That'll make it easier on all of us. 2x squared plus xy plus y squared plus stuff equals 0, because it doesn't matter what the stuff is. Okay, that would be 1. Okay, x squared plus 2xy plus y squared plus the same stuff, and x squared plus 3xy plus y squared plus the same stuff. All right. So I've got this situation here. It looks like I just wrote essentially the same equation 3 times, but it's not exactly the case, because in the first case here, right, we calculate 4ac minus b squared. That would be 4 times 1 minus 1 squared. That's 3, but mainly that's positive. In the second case, I have 4 times 1 minus 2 squared. That's 0. In the third case, I have 4 times 1 minus 3 squared. This is an ellipse. This is a parabola. This is a hyperbola. Oh my goodness. Yeah, that's why it was so important to understand this part. The xy kind of confounds things. And how does it work in general? Well, if xy is a dominant term, then it's going to be a hyperbola, because that's going to dominate. But really, it's also, I can have an xy term as long as the, a and the c are big enough. If this is 0, if this is not actually there, this is easy. If the xy wasn't there, then I just look and see, are a and c the same signs? Are they opposite signs? Is one of them 0? Those are all the things you did in lower level algebra. But the moment I threw the xy term in there, now I have to consider this. Okay, I just wanted to remind you, this is what we did in Calc 2 for a little while to be able to determine. Say, why did we do this in Calc 2? There's no calculus in this. You never took a derivative. You're right. Why did we do this in Calc 2? I didn't tell you this. What if I'm going to replace 0 with function. In other words, I'm going to replace 0 with z. That means all those conics you did were a level curve of this. In other words, if I replace that function with 0, that's one particular level curve. But if I leave that as is, that's now my z, if you will. I now have a three-dimensional surface whose cross sections are the conics. The reason you reviewed the conics late in Calc 2 was because you're going to use them now in Calc 3, but from a very different point of view. So when I'm looking at this, oh man, how the heck do I figure out what's going on, maxes and mins and everything else? Well, when we're working problems, we're not going to be limited to 2. We're going to work all sorts of exponents. But the results that happen when they're conics, we actually can extend to other shapes. Namely, if I have something that's, let's say, parabolic in nature, let's do my favorite one. Z is x squared plus y squared. Okay. You know what? I love this one because I can actually, well, I can draw it. Circular paraboloid. Is there a minimum z value? Yeah, it's going to be down here at the origin. In other words, where the vertex is, I clearly am going to have a minimum. Okay. If I have a closed shape, like a sphere, will there be a maximum value? Yeah, at the very top of the sphere. Will there be a minimum? Yeah, at the very bottom. Will all shapes have maxes and mins? No. The analogy I used the other day, I'm taking my blanket, I'm getting ready to make my bed, and I'm fluffing my blanket, I'm getting it, and then I let go, and it freezes in midair. So I have rolling peaks and valleys on my blanket. I'll have lots of maxes and mins. Okay, I'll have lots of peaks and valleys. So the question is, how do I find them? Well, it actually sneakily comes from that statement right there, even though we're not necessarily dealing with conics. So let me go up to here, and I want to show you something really cool. This isn't in the textbooks. In the textbooks, they actually just say, do this. There's never a why do you do this, you just do this. All right. Now, knowing that we need to take derivatives in order to find critical things, like in Calc 1, I need to take derivatives here. So the first thing you would do is you'd find when fx equals 0 and when fy equals 0. Okay, that's the very first thing you're always going to do. Whatever it is you're dealing with, you're going to take your derivatives, you're going to set them equal to 0, and then that will tell you the ordered pairs you get. You're going to do both of these simultaneously, and your results are going to be ordered pairs, x comma y's. So let's suppose that this is my result. This is called a critical point because it is an ordered pair. It is a point. It's a point on the xy plane, but the xy plane is where my domain comes from. Now, the next thing we're going to do is we're going to take the second derivatives. We're going to take the second derivatives, all of them, and then we're going to somehow do some weird, funky form of a second derivative test, but we're not exactly sure how we're going to do the second derivative test yet. So I'm going to go back up to this conic. Let me erase this stuff right here. The secret comes from the conic. If I said, what's fx? You'd say fx is 2ax plus by plus d. What you do is you'd set that equal to 0. Okay, you're not going to get a solution yet, but then you're going to take fy, which is, where are we? Bx plus 2cy plus e. You're going to set that equal to 0. Now what you have are two equations and two variables, and you're going to solve them simultaneously. You're going to get your x naught, y naught. Okay. Now I want you to notice something. What if I take the second derivatives? What is fxx? That's 2a. What is fyy? That's 2c. I'm sorry, this, something's not quite right here. This should be an x, sorry. That's my y. Okay. Fyy is 2c. What's fxy? That's just b. Now I want you to notice something. If I write fxx times fyy and I subtract the square of that, what a crazy thing. Why would I ever do such a thing? What am I going to get? 4ac minus b squared. Oh, wait a minute. In my original conic, on the XY plane, whether this was positive, negative, or zero told me what my conic section was. If I take the exact same thing now in 3 dimensions and I do partial derivatives, this quantity here is equal to this. I can still tell you what it is. But now instead of looking at the original 2-dimensional shape, I'm going to look at the second derivatives in order to determine this. And the same thing is true. The parabola, the ellipse, the hyperbola kind of results. Now, when I get into higher degrees and more complicated things, we're still going to do this. It's just my result might be different numbers. Because if I put 3rd and 4th powers up here, right, this will look a little different. But here's the key. I can only get extrema in certain situations. I can only get extrema, for example, in this case, if it were elliptical, circular, parabola, I can get extremes. But I can never get extremes with the hyperbolas. Now think about a hyperbola. Hyperbola is never going to have extreme. Well, why would circles and ellipses? Circles and ellipses are closed. There's definitely a highest and a lowest. Parabolas have a high or a low, depending which way it opens, at its vertex. But hyperbolas don't have any extrema in 2 dimensions. So in 3 dimensions, they're even worse. So we use this. Now, this quantity right here comes from someplace. It actually comes from a determinant. And I'm going to remind you guys, because a lot of you like using determinants for cross product, but almost everybody does it 100% incorrectly because you never actually learned how to do a 3x3 determinant. Sorry, but a 2x2 determinant is trivial. A 2x2 determinant is AD minus BC. This comes from a determinant. Now we know fxy and fyx. We know those are the same thing. This determinant is equal to this. This is called the Hessian. It usually start with a matrix, and then we take the determinant of the matrix. It's called the Hessian. If you're an engineer and you're going into your upper level, 3rd, 4th year gnarly physics classes and stuff, you get really used to this, and you do this in higher dimensions. You do this with 3x3s and 4x4s. Depends how many independent variables. See, right now, X and Y are my independent variables, so my Hessian would be 2x2. If X, Y, and Z were my independent variables, then my Hessian is 3x3, and so on and so on. We are never going to go in that direction. The Hessian is this quantity. For any function I give you of 2 variables, any function of 2 variables has a Hessian. And based on whether the Hessian is positive, negative, or 0, I can determine everything I need to know about the nature of my extremum. That's totally a cool thing because it kind of piggybacks off this. So now here's the one thing. The Hessian equal to 0 is the only time it's bad. You can do a second derivative test in Calc 1, and you took the second derivative at your critical value, and it was neither positive nor negative. It ended up being 0. That was possible. If your second derivative at your critical number was 0, it meant you actually didn't have an extremely, you had an inflection point. Well, it turns out in our situation, if this is 0, we say that it's inconclusive. Okay, I would have to really work hard to create a problem where this was 0. You're just not going to see 0. That's rare. So really it comes down to this. This tells me I have an extrema. This is pure evil. Okay, I'll explain why it's pure evil. It has to do with the hyperbola thing. So let me give you a simple picture, and I think I've illustrated this picture before. Okay, the hyperbolic paraboloid is kind of our 3-dimensional hyperbola. We sometimes call it, we say it looks like a saddle. Okay, so I'm trying to illustrate this. This is the hyperbolic paraboloid is that really crazy shape. And here's the way I like to think about it. Okay, these cross sections are all parabolas that are going up and down. And coming at you is the hyperbola. When I'm looking straight on, I see this point right here in 3 dimensions, and that clearly looks like the low. But now I'm going to stand and face the saddle. I'm facing the horse, either the front or the back of the horse. And I see all these parabolas And from this point of view, that clearly looks like a high point. From this point of view, this looks like a maximum. From straight on this way, it looks like a minimum. Now we know it can't be both. And so remember, we had a very clever name for this point. We called it a saddle point. Now we didn't do anything with it at the time, but we called that thing a saddle point. A saddle point is confounding because it appears from one point of view, it can be a maximum, but from a different point of view, it can be a minimum. Therefore, it's neither one. Okay, it's neither one. When your Hessian is negative, the ordered pair that produce, by the way, these are scalars, these are not functions. You've already evaluated them at your critical numbers or at your critical points. When the Hessian is negative, you have a saddle point. And a saddle point is not an extrema. It's a place in space. It's weird. And by the way, this is true even if it's not a conic. We still call it a saddle point because it has the same sort of behavior. From one point of view, different point of view. So what about this one? Well, I have an extrema if the Hessian is positive, but how do I know if it's a max or a min? Well, now go back to Calc 1. When you did the second derivative test in Calc 1, if your second derivative evaluated at a critical number was positive, it meant you were concave up. It meant you had a minimum. If your second derivative was negative at the horizontal tangent, it means you had a maximum. Well, we actually use the same reasoning here. The only way, by the way, the only way this can be positive is if my second derivatives are the same sign. Either they're both positive or they're both negative. If one of them was negative and one of them was positive, I would always get this result because I'd have a negative number minus something squared. So the only way I can get here is for fxx and fyy to be the same sign. So in this case here, either they're both, they're both positive or they're both negative. Well, if they're both positive, that means from all points of view, straight on from the side, from all points of view, I'm concave up. That would mean I have a minimum. If both of them are negative, then it means from all points of view, I'm concave down. I'd have a maximum. That's it. Now, do you remember in Calc 1, we had to determine whether something was a local maximum or an absolute maximum? That wasn't calculus. That was just looking at the behavior of the function. So when you had a polynomial, for example, when you had a polynomial of even degree, then you knew it went up on both sides. So therefore, there was no absolute maximum. If you had a polynomial of odd degree, you knew it went up in one direction and down in the other. So all extrema would be local. See, if I have a parabola, I'm going to have an absolute extrema. But if I have a cubic, usually my extrema are going to be relative or local. And that just comes from looking at the exponents and things like that. So that's the least complicated part. So let's do a couple problems now from start to finish to see how this process works, because there is some algebra involved. You're gonna have to roll up your sleeves. So let me start with something that's relatively simple, low level. Let's do f of xy is x cubed. Let's see, what do I want to do? I want to do x cubed minus y cubed minus 3xy minus 6. Okay, this is my function. Now I have no idea what it looks like. It doesn't matter, and it's not conic in nature, but I'm going to do the Hessian and do all that kind of stuff. So the first thing we're going to do is take our partial derivatives, first order partials, set them equal to 0. Excuse me. So fx is 3x squared minus 3y. That's it. Fy is negative 3y squared minus 3x. Now we're setting both of these equal to 0. So when I set both of them equal to 0, I need to find the simultaneous solution to the system. Well, one way I can solve for y and substitute back in, or I can solve for x and substitute back in. That's probably the easiest way. So in the first equation, looks like y would equal x squared. Okay, if I throw it on the other side. So if y equals x squared, let's go back to here, and then I would have negative 3x squared squared, that'd be fourth, minus 3x equals 0. Okay, so stare at that for a moment. If I factor out a negative 3x, then that leaves me x cubed plus 1 equals 0. And the sum of cubes can be factored. So that's negative 3x, x plus 1, x squared minus x minus 1. Now, that only has complex solutions. So let's look at these two. Clearly, this is going to be 0 when x is 0 or x is negative 1. Beautiful. So I have two different values that x can be. All right. Now, since to make this true, y had to equal x squared, there's going to be two different values of y. So let's write over here. So for x equals 0, y is going to be 0 squared. For x equals negative 1, y is going to be the square of negative 1. That gives me two different critical points. The first critical point is going to be 0, 0. The second critical point is going to be negative 1, 1. Okay? So that wasn't terrible. Now, solving the simultaneous system can sometimes get icky because it's very likely you're going to have x and y's in both. That's the reality. All right, now that I've got that, let me erase this. I need the space. So now we need to do our second order partials. So fxx is, looks like 6x. Fyy is, looks like negative 6y. And fxy or fyx, it's going to be the same thing, is negative 3. Okay. Now we have two different Hessians we have to find. So probably the easiest way of doing it is saying, okay, I need to evaluate these at 0, 0. I need to evaluate these at negative 1, 1. And then I need to plug them into the Hessian formula, or I can just do it like this. Here's the notation I like to use. The Hessian evaluated at 0, 0, just big H, is what? 0 times 0 minus, again, it's this evaluated at 0, 0 times this evaluated at 0, 0 minus the square of this evaluated at 0, 0. This is negative 9 or less than 0. What does that mean? That means I have a saddle point. Now, in Calc 1, critical values, critical numbers are x values, extrema are y values, but every now and then you had to identify an inflection point. So the inflection point was the ordered pair. Now I'm looking for extrema. Technically, I'm looking for the z values that are the high and the low. But we just came up with something, a saddle point. A saddle point doesn't have value, it's a place. So how do I answer the saddle point? Well, in this case, the saddle point will be the ordered triple. So the saddle point will be at x, y, and what is f of 0, 0? Looks like negative 6. 0, 0, negative 6 is clearly a point on this graph. Even though I don't know what it looks like, I know that point is there, and that point is a saddle point. How do I know it's a saddle point? Because the Hessian was negative. Now let's do the same thing for negative 1, 1. The Hessian for negative 1, 1 is, if I replace x with a negative 1, that's going to be negative 6. If I replace y with a 1, that's also negative 6. And then I'm going to square the negative 3. So this is 36 minus 9 or 27, which is, of course, positive. That means I do have an extrema. I'm going to have an extrema here. Is it a maximum or a minimum? Anybody want to try that one? Is my value going to be a maximum or a minimum? We haven't even found the value, but you can tell me if it's a max or a min right now. Those are both negative. Anybody want to yell it out? Max or min? What do you think? Both those guys are negative. No one wants to take a chance.
Negative? Minimum?
Maximum or minimum? I couldn't understand. What is that? What does the negative mean? It means it's concave down at both. Concave down at both means it's a maximum.
Maximum.
That's what I was going over before. So this means I'm going to have a maximum. Now, I don't know where what my maximum is yet, so I have to take that and evaluate it. So f of -1, 1, that'll be -1 minus 1, that's -2, plus 3, that's 1, minus 6, that's -5. Okay? This is the extrema. Now, this is you just said it's a max. Is it local or absolute? In Calc 1, I always do this. It's a blank max. It's definitely a maximum because my Hessian was positive and both of these were negative. So I was concave down from every point of view. Is it local or is it absolute? Well, I don't need calculus for that. Look at the function. If x grows without bound positively and at the same time y grows without bound negatively, then both of these are approaching positive infinity. So I'm pretty sure that -5 is not the highest point it ever reaches if it's approaching positive infinity. So this is definitely a local max. Is there a minimum of this graph? Turns out there's no local minimums, and if x grows negatively without bound while y grows positively without bound, this thing will approach negative infinity. So from one part of the world it's going up forever and another part of the world is going down forever, and it's got this one little peak. And it's got this one really evil saddle point. So the two pieces of information that we glean from here is that -5 is a local max and 0, 0, -6 is a saddle point. So you see there's a lot of Calc 1 analogy in this problem, but there's additional stuff we have to do because of the multiple variables. Okay, that's the first problem. Let's do another one. And one of the best things, like in Calc 1, I don't actually have to know what it looks like in order to make my conclusions. My conclusions are based entirely on the calculus, not on a picture. No, let's try one. Let's see, can we get something sort of diabolical here? I like diabolical. That one. Oh yeah, that one looks way nasty. Okay. All right, f of xy equals 4x cubed, excuse me, minus, I'm sorry, 4x cubed minus 8y cubed, almost that backwards, plus 6x squared minus 72x plus 384y minus 30. Yeah, like I said, diabolical to the end. Now, there's going to be a lot of work on this one. I got a lot of terms. So let's find our partials. Now, one thing you do notice about this one, though, this one's not going to be as hard as the last one for one simple reason. There are no xy terms. So why is that a big deal? Because that means the partial with respect to x will only have x's. Easier to set to 0. The partial with respect to y will only have y's. Again, easier to set to 0. I can do those independent of each other. That will make my life a little easier, actually. So fx is 12x squared plus 12x minus 72. Okay, let's go ahead and factor this in again. I think we can pull out a 12. And that would be x squared plus x minus 6. That's x plus 3 times x minus 2. That will equal 0 when x is -3 or +2. Beautiful. Next, fy -24y squared plus 384. Okay, I can definitely factor out a -24, and that would leave me with y squared minus 16. Not so bad. So y plus 4, y minus 4. So it equals 0, 4, negative 4. Now, I found these independent of each other. In the last problem, because there was a relationship between x and y, I think we had y equaled x squared. Then when I had an x, the y that went with it was automatic. When I had the other x, the y that went with it was automatic. I found these independent of each other. That means that each of these goes with each of these because there is no relationship right now between x and y. So I'm going to actually have 4 critical points. Yikes. That makes definitely more work for me. So let me do, I need to write them somewhere. Well, for now, I'll write them down here. So the critical points, the CPs, are going to be -3, -4, -3, +4. +2, -4, +2, +4. Now, any or all of those could be extreme. Any or all of those could be saddle points. I could have a mixture of extreme and saddle points. With that many, there's probably going to be a mixture. All right. Now, I'm done with first derivative stuff. So let's go ahead and do our second derivative now. I don't need this anymore. So fxx, that's going to be 24x plus 12. Fyy, that's going to be -48y. And then fxy, that's going to be 0. I like when that happens because that means my algebra is a little bit easier. So now we have to calculate the Hessian for all 4 of these points. Now you could, it is totally correct to do this. I'm not saying you shouldn't. It is totally correct to say at 3, -4, fxx of -3, -4 is, and then you calculate, and then do the same thing for fyy, then do the same thing for fxy, and then calculate your Hessian. That's correct. Man, it's a lot of writing though. I'd rather just do it one time. So I'm going to write it like this. The Hessian evaluated at -3, -4. The Hessian evaluated at -3, +4. The Hessian evaluated at 2, -4. You do have a calculator. You don't have to do any of this in your head. All right. So at -3, -4. When I put in a -3 for x, that'd be -72 plus 12. That's -60. When I put in a -4 for y, that's -48 times -4. So that'd be +192, and then minus 0 squared. Okay. Here's my calculator. I know that's a large negative value. Oh, here's my calculator. Always calculate just to be careful, but it's really the sign, not the size of the value that matters. So this is -11,520. All that really matters is that it's negative. Okay. Next one, -3, +4. So that's going to be -60, -192 minus 0 squared. I don't need a calculator to tell me that one's positive. Okay. Next one, +2, -4. So it's 48 plus 12, that's +60. The -4 would make that +192 minus 0 squared. Of course, same value. And then the last one, 2, 4, it's going to be +60, -192. So clearly we can identify we are going to get 2 saddle points. We're going to get a saddle point because of that and a saddle point because of that. In 2 different places, I've got a negative Hessian. Okay. So we will go ahead and identify our saddle points. And now I need to erase a little bit more. We're done with this, so I'm going to erase this. So therefore, let me write down the saddle points. we have saddle points at -3, -4, and we have to still calculate it. And at 2, +4, we still have to calculate that. So get out my calculator again. I'm going to put these numbers into there. All right. So negative. I didn't mess this up. And by the way, I may have messed this up. I believe I got -1188. Okay. And I'll do the same thing for 2, 4. And I get 906. Again, if I didn't mess that up, always double check on the calculation. So these 2 places in space, these are not values, these are places. They're addresses. Now, I also have 2 extrema. Maxes or mins, or how do I know? Well, let's go back to here. This is an extrema because the Hessian's positive. Both of these values are negative. That means I'm concave down at both of them. That means I'm going to have a maximum here. All right. So let's say, let's write it like this. F of -3, 4, which equals, so we need to, -3, 4, we need to put that in there. In the right place here. Yeah, 6 and 9 plus. Oh, I was using orange before, sorry. 1156. And we just said this is a maximum is blank max. And similarly, I hate to do this, but I think I'm done with this really anyway. You identified this one as well. So F of 2, -4. So let's figure out what the Y value there is. Got a -1142. And again, because both of these were positive and it's an extrema, that means I'm concave up from every point of view. So that's a minimum. Okay, so similar to the last problem, if X is growing positively without bound and at the same time Y is going negatively without bound, then both of these are going up forever. So that means there's no absolute max. So this has got to be local, as is the case most of the time. And then similarly, if X is going negative without bound while Y is going positive without bound, this is going to go down forever. So in this graph, we have 2 saddle points and we indicate them with an ordered triple. We have 2 extrema. This value is the local max. This value is the local min. Okay, so don't stop here. Actually identify what is the value of the extrema. That's kind of important. Now, we're just looking at graphing stuff. Can we actually use this to answer a question, maybe a physical quantity? Yeah, we do stuff like this all the time in calculus, and we sometimes forget that we do stuff like this. So I want to do a fairly simple problem. Simple, I guess that's relative. In in Calc 1, we do a lot of stuff where we might, maximize or minimize. In Calc 1, we did things like you have this much material, construct, the box with a square base that has the least surface area or the most volume, just whatever. You did things like that all the time, but you could only do it in Calc 1 when you had one independent variable. Now we can do it for more than one independent variable. So the problem that I have, and I have the evil problem that I've created. All right. I make boxes, and you have to buy my boxes to put your stuff in to ship it in my boxes. So when you have your stuff takes up a certain amount of volume. So you might say, all right, Mr. Brown, I need a box that has this much volume, and maybe my volume is this many this many cubic feet, or this many cubic centimeters, this many cubic meters, but I need a box that has a certain amount of information. Okay, so you're buying my box that has a certain volume. Now I got to make the box, and I'm trying to save money. So if my box has to have a certain amount of volume, then I want to use the least amount of material as humanly possible, because it's expensive. And maybe it could just be a simple cardboard box. So here's what I want you to think about. We're going to make a box. And by the way, the box, there's nothing about the box that indicates anything has to be square. It's just a box. Okay. And if you look at all the boxes you have around the house, I mean, your boxes are rectangular in general, not square in general. So I have a box. Let's say that side is X, that side is Y, and that side is Z. So you have this is technically a rectangular prism, okay? So you have a rectangular box without a top. I just want an open box. It's a container that I want to be able to move stuff in, of volume, let's say, so what number did I want to use for volume? Hold on a second. A volume, maybe, trying to come up with a number that's nice. 32,000 cubic centimeters. That sounds like a lot. It isn't. It isn't a lot. Okay. A cubic meter, right? 1 cubic meter is 1,000,000 cubic centimeters, 100 by 100 by 100. So 32,000 cubic centimeters is actually a really small box. Because remember, you're taking side times side times side kind of thing. Okay. This is the volume. We want to minimize the surface area, because I said I want to use the least amount of material as possible. Well, the material that I'm making the box is area, not volume. I don't take a piece of cardboard and say that's a certain amount of volume. I say that's a certain amount of area. Then I construct the box and calculate the volume. So what would the surface area of this box be? We said it has no top. I'll just call it area. My area is going to be, well, the base is going to be X times Y. The front face is going to be X times Z, but I have two of them, a front and a back. And the side face, have two of them, is going to be 2YZ. All right. I want to minimize this. Well, the very fact that I want to minimize this absolutely means I have to take a derivative somewhere along the line. Problem is I have too many variables. Yikes. Anybody got an idea what I need to do next? What's the volume of my box, by the way? Anybody? What's the volume of my box? In equation form.
X times Y times Z.
X times Y times Z equals 32,000. I got too many variables here. I have X times Y times Z equals 32,000. Any good ideas? Any good ideas there? You did this in Calc 1, something similar.
Z equals 32,000 divided by XY.
I like that. By the way, would it have mattered which one I picked?
No.
No. It's I think the funny thing is, I think all of us would have probably made that choice eventually, but it actually does not matter. Now, why do I want to do this? Because when I substitute back in, now I will have a function of only two variables, and now we can use the math we just learned using the Hessian and all that. With 3 variables, no, I can't do that with 3. With 3 variables, this is a way more complicated problem from beginning to end. We're going to address that one on Tuesday. But if I can make this a 2 variable problem, which I'm now going to do, I think I did that right. Okay, everybody see that? Now, let's simplify this. Well, the x's will clearly cancel. So that'll be plus 64,000 over y. And this y's will cancel. That'll be 64,000 over x. This is my area, and all of a sudden, I mean, that's not wonderful, but that doesn't look nearly as scary, does it? Because we got some nice simplifications. So now what I've got to do, I've got to take some derivatives. I got to set them equal to 0. I got to go the whole 9 yards. Now, are there restrictions on x and y, by the way?
It can't be, both can't be 0.
Keep going.
I guess they couldn't be 0 anyways, because they're a side length, right?
Well, if there were 0, that would mean I'd have a 0 volume. What else can't they be? Can't be negative, right?
Negative, yeah.
So would you agree that x and y have to be positive?
Yes.
Yes. Do they have to be integers?
No.
No.
There's an infinite number of values I chose here. Almost all of them would produce irrationals. Yeah, no, they don't have to be integers, but they do have to be positive. And I'm pointing that out is because what if you do all of the math and you solve and you get an x is -5 or +7? Well, you say, well, -5 is outside the possibility. It's called extraneous. You would only use the positive because you can't get a negative answer. Do you remember when we did the projectile motion problems and you found the time it took to hit the ground? You got a negative time and a positive time. You didn't do anything wrong to get the negative time because a negative solved the equation, but that's not a possible answer because you're saying in the future when we'll hit the ground, time can't be negative. So you threw that out as extraneous. Same thing here. If I work this problem and I get a negative solution, that's extraneous. Now, the problem is if I only get a negative solution, that means I probably made an error. But it's because clearly there has to be a best size. There's an infinite number of shapes that will produce this volume. We want the one with the smallest surface area. There's going to be one with the smallest. So now I need to take partials here. In a moment, I'm going to have to erase up top. I'll start here. So AX, that'd be Y, that'll be 0, minus 64,000 over X squared. AY, that will be X minus 64,000 over Y squared. Oh, I kind of like the way this is looking. Okay, now I'm making both of these equal to 0. Yes, I could set them equal to each other, but that really wouldn't be useful. Using substitution would be way more useful. So go back to here. This says that Y equals 64,000 X squared. Now what I want to do is take that Y and just insert it there. The reason I want to do that, I will then have one equation with only X's. Let me go ahead and not my favorite step, but I need to do this. Okay, so let's go ahead, change pens here. If I insert that there, then I will get X minus 64,000 over the square of this. Okay, well, that's going to be an X to the 4th that will clearly make it to the top. And one of the 64,000s will cancel. So that's going to be X to the 4th over 64,000. Okay, remember the whole thing equaled 0. So I can factor. In fact, very specifically, I want to factor out 1 over 64,000 times X. This will make my life a little bit easier. If I did this correctly, if I factor that out, that will leave me with 64,000 minus X cubed. Okay, you with me so far? And I believe I've made a pretty good choice of my volume because, again, the reason I'm doing this makes this factoring a little bit easier. This is 40 cubed. Ooh. In fact, let me go one step further. Rather than factor that out, let me factor out the negative. That'll make the factoring easier. Let me factor out a negative number there. I think that'll make our algebra easier. So if I factor out a negative, then it'll be x cubed minus 64,000 or 40 cubed. And the difference of cubes has a really simple formula. That's going to be x minus 40 times x squared plus 40x plus 40 squared. This only has imaginary, or excuse me, complex solutions, because we know a difference of cubes is only going to have one real root. So when I set this equal to 0, there's an x here, I have two possibilities. What are they? X equals 0 or x equals 40. Again, now, is x equals 0 a possible answer? No. X equals 0 solve this equation, but it actually can't solve this because we already said the x has to be positive. So we go like this. That's not a possible answer. X equals 40, that might be the answer. I don't know. Let's see. There we go. If x is 40, then what's the value of y? If x is 40, well, let's see. Then y will be 64,000 divided by the square of 40. Y will be, oh my gosh, 40. That's not the final answer, but that means that the base of my box must be square. Now, does that shock anybody that the best case scenario would have a square base as opposed to maybe a long, narrow, thin base? Yeah, square base kind of made sense. You could not start the problem by assuming square base. That would be dangerous because that isn't necessarily going to be true. Now, if x and y are both 40, we still have to find the value of, I erased it. What was our original volume? Oh, original volume was 32,000. Sorry, I don't remember what it was. Z was 32,000 over XY. So in this case, what's the Z? It's 32,000 over 40 times 40, and that should be 20. So right now we're not done. We don't know if this is the best case scenario. Right now, we've got that X and Y are 40 centimeters. Z is 20 centimeters. That's what we have at this moment. But we still don't know if that's the best. We still need to do the Hessian. You say, what do you mean we don't know it's the best? Isn't it automatically the best? No, it's not. Just because you've got something as an answer doesn't mean it's the best answer. In fact, it could be the worst answer. I don't know. If you take a derivative and you set it equal to 0, does that mean you get an extrema? Neither a max nor a min. It's an inflection point. The three-dimensional analogy of an inflection point is a saddle point. In other words, this could be a saddle point. You don't know. Now, you suspect it's probably the answer, and you're probably right. But in the previous problem, we got 4 points, or I should say we had 4 critical points, and 2 of them produced saddle points. We didn't know that. But if you assume that automatically there were going to be maxes and mins, you get into trouble. So how do I know what my final answer is? Well, now we got to do the Hessian. And did I erase everything? Hopefully I didn't erase everything. So let me go back. My AX, if I did I write it down anywhere, was y minus 64,000 over x squared. Is that right?
Yeah, that's right.
Yeah, okay. All I wrote down was my original function. I didn't actually do the problem, so I'm trying to remember what they were. And this was, okay. So now let's do all the second order partials. Those actually won't be difficult because that'll go away. Think of that as being raised to the -2. So this will be positive 128,000 over x cubed, AYY 128,000 over y cubed. and a XY will be 1. Oh, I like that one. So we only have one critical value. I don't need this. You guys have been writing stuff down, so you can help me if I forget or something. I tend to forget things. So the Hessian at 40, 40, 20, or I'm sorry, just 40, 40. Sorry, we just have the XY so far. Is okay. 40 cubed, 64,000. So I think that's just 2. 40 cubed, that's 64,000. So that's just 2. Oh, wow. After all of that, our Hessian is nice. That's why you don't do the Hessian as a function. You do the Hessian as a value. So if my X is 40, 40 cubed, we said it's 64,000. So this is just 2 and so on. That's 3, which is greater than 0. Yes. That means we have an extrema. Now, is this the best or the worst? Remember, we are trying to minimize. Be careful. When you take a derivative and set equal to 0 and you're looking for a min, you could actually find a max and vice versa. Oh, so how do I know? Because both of these are positive. That means I'm concave up from every point of view. That means it's the minimum. Okay. Therefore, X equal 40, Y equal, I should say centimeters, because these are units. Sorry. X equal 40 centimeters, Y equals 40 centimeters, Z equals 20 centimeters, gives the minimum surface area. I like this problem. It was kind of busy, but it was not difficult from a geometric standpoint, and it really wasn't terrible from a calculus standpoint. But if I was trying to minimize the surface area of the box, what you can't do is say, well, let me think of all the different ways I can have a box be the following volume, and I'll just see what's the surface area of each one. You're never going to guess an answer that way. You see, was there any reason that our X, Y, and Z even had to be rational numbers? What if they were irrational numbers? I said 32,000. If I had used almost any other number, it would not have worked out so pretty. Okay, I got kind of lucky. I just sort of guessed. I knew something in that realm might work really, really, really well. So here's an example of how you use the Hessian to find your extrema. That's as far as I want to get today. Now, next day, we're going to look at a different way to find extrema. And we're also going to be able to find extrema when there's even more than 2 variables, which is really crazy. So an alternate way. And this is all part of optimization, which we considered the most important application in Calc 1. Well, we still considered it probably the most important application in Calc 3 because it's the only way usually to do things that involve money. In other words, I want to maximize my revenue or minimize my costs. I want to maximize the amount of miles I travel with a fixed amount of time. I want to minimize the time it takes me to travel when I have a fixed number of miles I have to travel. These are all things that are optimization type problems, and this is the math required. So let's go ahead and stop here.